May 1943, Dessau Airfield, central Germany. Inside a reinforced concrete hangar designed to survive engine explosions, a single aircraft rested under harsh industrial lights. Its aluminum skin had been stripped away, exposing fuel lines, wiring, and structural ribs like bones beneath flesh. This was not a frontline fighter. It was an experiment, a gamble, and perhaps Germany's last technological hope. Standing beneath its wing was Hans Werner Lerche, a 31-year-old test pilot whose experience bordered on legendary. He had flown captured American aircraft, experimental prototypes, and more than 60 different aircraft types. He understood machines the way surgeons understand anatomy. On this day, Lerche had been summoned for one reason only, to discover why Germany's most advanced aircraft engine was destroying itself. By May 1943. Germany's situation was already grim, though no official communique would ever admit it. American factories were producing hundreds of aircraft every month, while Allied bombers systematically dismantled German industry. The Luftwaffe was losing pilots faster than training schools could replace them. Fuel shortages limited flight hours. Spare parts vanished as rail lines and factories were bombed flat. Yet amidst this collapse, German engineers had done something extraordinary. They had built the world's first operational jet engine. The Junkers Jumo 004 mounted under the wings of the new Messerschmitt Me 262. It promised a future where speed alone could dominate the skies. Whether that future could survive reality was now Lerche's responsibility. The Jumo 4 represented a revolution in aviation. Unlike piston engines whose roots stretched back decades, this machine worked on entirely new principles. Air was drawn in and compressed through an 8-stage axial flow compressor, then mixed with atomized fuel and ignited in combustion chambers, burning at temperatures approaching 900 degrees Celsius. The resulting exhaust drove a turbine spinning at immense speed, which in turn powered the compressor. It was elegant, compact, and powerful. On paper, it was flawless. In practice, it was fragile beyond anything the Luftwaffe wanted to admit. The original prototype, the Jumo 004A, had performed impressively during controlled testing. It had demonstrated running times approaching 100 hours on the test bench. But it relied on materials Germany no longer possessed in sufficient quantity: nickel, cobalt, and molybdenum, metals critical for producing turbine blades capable of surviving extreme heat and cyclic stress. By 1943, these materials were being diverted to tanks, artillery, and armor plating. Germany faced an impossible choice: either build a limited number of reliable engines or redesign the jet to use cheaper materials and produce it in large numbers. The decision was made under pressure, and the result was the Jumo 004B. The 004B looked identical from the outside. Inside, everything was compromised. Exotic alloys were replaced with chromium-based steel. Turbine blades were welded rather than forged. Cooling was achieved by bleeding compressed air through blade roots instead of using heat-resistant metals. The calculations were clever, the engineering ingenious, but the margins were razor-thin. Time between overhauls dropped to 25 hours. In theory, this was acceptable. In reality, it was catastrophic. No fighter engine in history had ever been designed to die so quickly. Lerche climbed into the cockpit knowing all of this. He had been briefed thoroughly. Above 8,000 feet, something fundamental went wrong. Vibrations appeared. Temperatures climbed. Engines failed without warning. His task was to feel what instruments could not yet fully explain. With 45 minutes of fuel on board, he taxied to the runway. Twin jet engines spooled up with a sound unlike anything piston aircraft produced, a rising scream that felt more electrical than mechanical. The Me 262 surged forward, lifting effortlessly into the air. Almost immediately, Lerche felt it. Not the rhythmic vibration of pistons or propellers, but a deep, unsettling tremor flowing through the airframe like a living pulse. As he climbed through 10,000 feet into colder air, the vibration intensified. Gauges trembling, control stick quivering, the aircraft began to feel unstable in a way that defied traditional experience. At 15,000 feet, the engines entered the exact regime engineers feared most. Inside them, metal was being pushed to its absolute limit. The problem was resonance. At certain speeds and temperatures, combustion pulses aligned with the natural frequency of the turbine blades. Each ignition pushed the blades slightly out of phase. Each rotation made the oscillations worse. The blades did not snap instantly. Instead, they began to suffer microscopic fractures at their welded roots. These microfractures could not be seen, detected, or repaired quickly. They accumulated invisibly until catastrophic failure became inevitable. The engine was not designed to suddenly explode. It was designed to wear itself to death. At 18,500 feet, Lerche leveled off. The vibration changed character, becoming more rhythmic, almost musical, a high-pitched whine that resonated through his bones. Engine temperature climbed past 850 degrees Celsius, then higher. The cooling air intended to save the turbine blades was itself superheated. Metallurgically, the blades were entering a state where fatigue accelerated exponentially. Lerche understood what was happening without seeing a single crack. Decades of flight experience told him this machine was consuming itself from the inside. The comparison with Allied engines was impossible to ignore. American aircraft engines were designed with enormous safety margins. The Allison engines powering fighters like the P-47 Thunderbolt were rated for hundreds of hours between overhauls. Some exceeded 1,000 hours. American industry could afford wasted material, redundant strength, and conservative design. Germany could not. Every gram of metal was weighed against shells, tanks, and rail lines. The Jumo 004 was built not for endurance, but for desperation. Fuel consumption only reinforced this reality. At cruise power, the Jumo 004 burned more than 15 times the fuel of a piston engine. A Me 262 carried enormous fuel tanks yet could barely remain airborne for 2 hours. Range was limited. Training flights were restricted. Every takeoff consumed precious engine life. Speed was extraordinary. The aircraft could exceed 540 miles per hour, but speed alone could not sustain air superiority. After 38 minutes, Lerche began his descent. The engines were still running, but he knew their internal clocks were ticking faster than any instrument could display. Temperatures hovered near the limit. Throttle movements had to be smooth and deliberate. Any sudden change risked flameout or blade failure. The runway came into view like safe ground after crossing thin ice. Landing gear extended. Dive brakes deployed. The Me 262 touched down smoothly, rolling to a halt amid waiting engineers. Lerche shut down the engines and climbed from the cockpit without ceremony. He went directly to the debrief room. The data confirmed what he already knew. Turbine resonance occurred precisely within operational flight envelopes. Metal fatigue accumulated rapidly. Under ideal conditions, engines might survive 25 to 35 hours. In real combat conditions, rapid throttle changes, sustained high power, evasive maneuvers that lifespan dropped to 10 or 15 hours. Each sortie pushed the engines closer to death. The implications were devastating. A German pilot might fly 5 combat missions before needing a complete engine overhaul. An American pilot could fly dozens. This was not a matter of bravery or skill. It was arithmetic. Industrial capacity versus exhaustion. The Luftwaffe command understood this immediately, and they understood something worse. There was no solution. Improving the engines required materials Germany no longer had or time Germany could not buy. Production surged regardless. By late 1944, Me 262 airframes were being completed faster than engines could be delivered. Hundreds of aircraft sat idle, incomplete, waiting for Jumo 4s that arrived too slowly and failed too quickly. By war's end, over 1,400 Me 262 airframes had been built, yet fewer than 300 ever flew operational missions. The bottleneck was never design talent. It was industrial collapse. Hans Werner Lerche survived the war. He lived quietly, writing later about his experiences without bitterness. He understood the truth behind that. Flight in May 1943, the Jumo 004 was not a failure of engineering. It was the limit of genius operating under starvation. Germany had invented the jet age, but invention alone does not win wars. Sustaining technology requires resources, margins, and time. America had all three. Germany had none. The air war that followed was not decided by faster aircraft or braver pilots. It was decided by factories, raw materials, logistics, and endurance. 25 hours versus 500 hours? That equation sealed the outcome long before the final bombs fell. The jet arrived too early for Germany and far too late to change the mathematics that ruled the skies. Thank you for listening.